session. So session 2B is on the CaMa-Flood development papers. And I'd like to invite 6 presenters, Menaka Revel, Dirk Eilander, Toby Matthews, Wen Chaomar, Pragat Modi, and Shudon Zhou. So Pragat, could you, Menaka, could you please share your screen and start your presentation?
Yes, sir. Hope you can see my slides. Yeah, give me a second.
I think maybe you need to restart Zoom. So can I? Okay, it works now.
Okay. Good afternoon, everyone from Japan and others from somewhere else. So my name is Menaka, and we have done few work on data assimilation. So the one we publish is trying to assimilate the observations from the real satellite altimetry data. So to the KM flood model. So first of all, we thought of developing a data assimilation framework for the global scale, fairly thinking about the SORT mission and the unique capabilities of the KM flood model, where we can simulate the water levels throughout the world. We thought of like how we can combine the satellite altimetry data to the global river model like KM flood, and we developed the framework using creating a runoff ensemble and KM flood as the core of the data assimilation framework, and using some techniques of the empirical localization of developing the data assimilation techniques, and using the observations, we have developed this framework to work in the global scale. And in the previous studies, we have found that it can work in the global scale and give us good results. So I will slowly talk about a little bit about the data assimilation technique and the development what we have done. We have developed a method to capture the correlated observations in a local patch shown in this picture, like in blue color. And to find this kind of a local patch area, we done a little bit of statistical analysis, and we found this using the observed data, and later we found that the method is better than using conventional data assimilation techniques, and we found our newly developed method have a much better accuracy than conventional methods. So moving on to that, when we look at the satellite altimetry data compared to the water surface elevation simulated by the KM flood model, there were a few discrepancies, like for example, there can be biases can be seen between the observed values shown in these hollow circles with the simulated values in the red. So in such kind of cases, we need to remove the mean from both of the data series to make it an anomaly. So likewise, we have to do a little bit of interventions to get a good assimilation. So here we tested 3 different data assimilation techniques, such as direct assimilation. We assimilate the direct values, and in the anomaly assimilation, we remove the mean from both observation and the simulations and try to assimilate the anomalies, and then we normalize the values by removing the mean and dividing by the standard deviation to make the range comparable to each other. So in the results section, we found that the normalized data assimilation method works well, mostly in the Amazon basin here, and we found that the particularly in the downstream of the Amazon, is very well assimilated by using the normalized value. Basically, these are due to the characteristic errors of the KM-Flood model, which may be can be developed in the future, such as the river bottom elevation or the river width and the elevation along the river as well. So I think this is a great opportunity. Like, we can improve this method to the future, where we have the SWOT observations, and we can incorporate those real SWOT observations to improve the data assimilation and the river discharge in the global scale as well. So that's all of my presentation. Thank you.
Okay, oh, thank you very much, Menaka. So yeah, this was a great work, and now SWOT is launched. So I'd like to see how this framework works with the real SWOT data. Okay, oh, thank you very much. So I'd like to move to the next presenter. So Dirk, could you please share your screen and start presentation? Oh, it seems your mic is not working. Oh, Dirk, your mic is not working. Could you please check?
Sorry for the problem with my mic. Is this better?
Oh, yeah, it's working now.
All right. I'll turn off my headphones. Sorry for that. All right. Thanks again for the invitation, Dai. This is work I did together with Yamasaki-sensei and others a few years back, looking at compound flooding. So where most of the applications with CaMa-Flood have focused on riverine flooding, here we were also interested to see how it does in a coastal environment where not only rainfall and river discharge, shown in green and purple here, is important, but also the interactions with coastal water levels, as shown with blue here, which can exacerbate the flooding, shown in the red area here. So in a first paper at the global scale, where we coupled CaMa-Flood with the global tide and surge model, we found that in roughly 20% of the river deltas that we investigated, compound flooding was, actually there was the dominant flood driver in those areas. But these results are all based on CaMa-Flood, so based on 1D water levels in the estuaries, basically. And we wanted to also understand better what it means in terms of the full flood extent and inundation. So therefore, we developed a not a global model, but what we call a globally applicable framework. So this is basically a fully automated setup based on various global data sources about topography, bathymetry, etc. Forced with also globally available forcing data for rainfall from Area 5 in this case, and the global tidal search model again for downstream boundary conditions, and CaMa-Flood for upstream discharge boundary conditions. This is fully automated using HydroMT, Hydro Model Tools. This is a package, Python package that we developed and now supports various models in automated model setup from various data sets. And here, all these different data sets and boundary conditions come together in the Sphinx model, that is a 2D hydrodynamic model, which really specializes in compound flooding in coastal deltas. So the model setup is as follows. On the left picture, you see the rivers for two basins, the Pungwe and the Busi. We are here in the east coast of Africa, in Mozambique. which are simulated by CaMa-Flood, and then in the black rectangle, that area, basically the delta, we simulate in the Sphinx model, which is shown on the right. There are 3 or 4 locations rivers are flowing into this domain, and there we take the data from CaMa-Flood, and downstream at the ocean we take outputs from GTSM to force this model. We validated this model for tropical cyclone Idai that happened in 2019. This caused large flooding, as you can see in the Sentinel observations. All the red areas were flooded. We compared how the Sphinx model performed compared to using only CaMa-Flood, like we did in the previous global paper. So in figure A, in the middle, you see the results for CaMa-Flood, and you see some orange patches, which are areas where we did observe flooding, but CaMa-Flood was not able to simulate it. And in red, where CaMa-Flood overestimated it. And on the right, you see the same for Sphinx. And you notice that there's much less orange. And we think this is because although we do use the bifurcation scheme in CaMa-Flood, it is still a quasi 1D model, and it in very flat deltas, it may still lack sufficient connectivity in the delta compared to a fully 2D model like Sphinx. And with this type of modeling, we can also investigate using scenario analysis, where we force the model only with discharge, only with downstream boundary conditions, and together what the effect is of the compound flooding. And we find that for this particular event in this area highlighted in red, the water levels were much higher. So this is really the effect of this compound effect that we found here. And where you find this effect largely comes from how the forcings basically interact and compound over time. So in this case, the surge was actually much earlier than the discharge flood peaks. In different events, Eloise, that was in 2021, we did a similar, the same analysis. And we found that actually the compound area here highlighted in the darker purple and orange colors extends much further downstream because of the tide and surge happen much more closely together. So in general, compound flooding is important to account for in coastal deltas. With the framework that we developed, we can do this anywhere globally. And using HydroMT, we can also readily improve it with better data sets. For instance, the local bathymetry or lack of bathymetry data is still a challenge in many estuaries globally for accurate compound flood modeling. We've also extended this into a flood risk assessment that was published also in 2023. And currently, we're also looking into the performance of surrogate models to simulate compound flooding, which I will present at EGU this year. With that, I'd like to thank you, everyone, for your attention.
Okay, thank you very much, Dirk. So yeah, we know CaMa-Flood is not perfect, and this kind of a coupling framework is very helpful to understand the risks in complex area like Delta. So we are looking forward to see the progress. So thank you very much, and I'd like to move to the next talk by Toby Mashu. Could you please share your screen?
Hi there. Is that visible?
Yes, please start.
Great. Thank you very much. Thank you very much, Dai, for the invitation to present at this briefing. It's a great honor, actually. Okay. I've probably done too many slides, so I'll go through this this quite quickly. My name is Toby Matthews. I work at the UK Centre for Ecology and Hydrology. This is a UK-based research institute. We're spread across 4 sites in the UK, and we have an international office as well. We look at terrestrial and freshwater ecosystems. I've got 2 sections in this talk. I'll talk about global wetlands, the work that I was doing in 2022, and then I'd like to talk about some more up-to-date work that I've been doing to try and develop CaMa-Flood. So I've been looking at wetlands for a long time, and I did this study with Dai and others back in 2022, looking at global wetlands. So I chose various wetlands across the world, mostly focusing in the tropics. And I was using an earlier version of CaMa-Flood, version 3.95 or 3.96, I think it was. And I ran that over all of these wetlands that you see there. I was then comparing the outputs from the inundation that we got with some downloadable inundation product called JULES, which is a French product that's highly regarded. The runoff was predicted from a land surface model called JULES, the Joint UK Land and Environment Simulator. And then I took those runoffs and put them into CaMa-Flood, and then ran CaMa-Flood to get the inundation. And so you can see, to cut a long story short, if you look at the Sud, which is a big wetland in South Sudan, we have the observations on the left from the remote sensing product, and we have the predictions of the model on the right. And it looks like here that the model overestimates inundation across pretty much all seasons, as you can see from this plot. However, if you look at a different wetland, the Pantanal in South America, it looks like we get the opposite. We get CaMa-Flood underestimating inundation. Then if you look at a third example, the Cuvette Centrale in the Congo, it looks like here that CaMa-Flood gets it approximately right. I'm summarizing here, but I was using the standard statistics like Nash-Sutcliffe efficiency and Kling-Gupta efficiency to measure these things. The fit appears to be much closer, but there's a lot hidden by the scale because this wetland is much larger than the Pantanal. And so I asked myself, are we missing some fine-scale processes? To take another example, there was a big flood in the US near St. Louis in 1993. How much of this event is it possible to simulate using the modeling tools that we're using? The river flow regime, are we getting that right? Does the inundation stay as long as it should after it's been predicted? There's evaporation from the inundated area. There's interactions with the vegetation. There are things like methane flux from wetlands. All of these things are important, and not all of them are modeled with the tools that we're using here, obviously. And you can run, I'm not sure whether these videos will work on a screen share, but if you run CaMa-Flood predicting this particular flood event, you can see a pulse of water comes down the Mississippi from the north. The star is where the city of St. Louis is. And you can see that it seems to get it right, approximately right, but the spatial scale that I was working at here was probably not enough to pick up the fine scale processes. If you take a step back and look at this globally, I can run this simulation as well. This is a bit of a complicated plot, but what I've done here is I've shaded in dark blue the precipitation, and then in yellow I've overlaid the inundation. So if you choose your favorite part of the world and focus on it while I play this again, you can see that the precipitation steadily drifts from north to south as you go over the seasons, and the inundation follows it with a kind of lag time. And that's what you would expect. CaMa-Flood is doing this very well. And in fact, it works a lot better than the default river model that we have in the JULES land surface model. And even without coupling to the ocean, we can capture the majority of large-scale effects here. So this was more or less where we got to in 2022. We suspected that fine-scale processes were missing, and of course we knew that larger-scale processes like coastal exchange were certainly not simulated. So my next opportunity to move forward on this came when I got involved with a project called Chamfer in the UK, and this looks at UK coasts. So coasts are very important. We've got a big, there are a lot of international drives to look at coastal processes at the moment. These have been mentioned actually in Dirk's very interesting talk just before me as well. We've been working on this in the Chamfer project. It's got a UK focus, but we're looking at the coastal zone. There is a lot of the focus of the Chamfer project is to look at impacts rather than specifically developing hydrological models. And this is all part of current attempts to quantify blue carbon and things. So I won't go through any of this. I liked this example from an old project called Charim, which was, I should stress, I wasn't involved with this project, so I've shamelessly stolen their slides to put it in this presentation. This Charim project was run by some colleagues at the University of Bristol in the UK, and they mapped 3 types of flooding: pluvial, fluvial, and coastal here. This is the country of Belize in Central America, and you can see their 3 plots here. In the JULES model, even if we're using the CaMa-Flood routing, we can get the fluvial and pluvial flooding, the first 2 on the left there, but we don't have the capability to include coastal inundation, which is the one that's green in the middle panel. And but we do have the ability to put this in if we make some modifications to CaMa-Flood. So CaMa-Flood is brilliant because partly it has this fantastic local inertial approximation, which has got the backwater effects. This was mentioned in the last presentation. So the RFM is the river flow model that's the standard model in JULES, and that makes a lot of approximations. It effectively excludes all these higher terms of the momentum equation. CaMa-Flood only excludes one of them, so it's a much more accurate representation of what's going on in rivers. Then how do we include the coastal dynamics? We've got a lot of things going on in the ocean, and I'm collaborating with the National Oceanography Centre in Liverpool in the UK, and they have got a model of the ocean, or in fact several models. We're putting together this kind of coupling arrangement where JULES and with CaMa-Flood inside it is the hydrological model that does the rivers on the land surface. This is coupled with NEMO, which is an ocean model which takes into account things like bathymetry, sea level rise, and storm surges. And on top of that, you have to couple to a third model called WaveWatch, which handles the wave effects on top of that. I have this slide from colleagues at NOC. It's very difficult to put this coupled model paradigm in together. You have a lot of physics to be included on this. We're missing some of it. We don't have all of it together at the moment, but we're very close to getting this in the Chamfer project. And it's very important to think of, I'm sure I'm losing time, but it's very important to think of coastal exchange points. So this is the east coast of England here in this illustration, and you have to identify points where the land surface is going to communicate with the ocean, which is effectively at all the estuaries, all the larger estuaries. If you calculate where the estuaries are using the standard CaMa-Flood ancillaries for river directions, you get 18,500 estuary points across the world. But the number changes if you use different ancillary files, obviously. And it's very important where these CEPs are, the coastal exchange points. I've got a good example here from colleagues at the UK Met Office. This is the top of South America, you can see here. And when they were calculating their CEPs originally, they were using a low resolution ancillary files called N96. Doesn't matter the details, but effectively you can see the river outflow was appearing in the top left of these panels. The river outflow was appearing not at the estuaries of the rivers, but actually 100 kilometers into the ocean. And that meant when you ran the simulation using the ocean model, you got the dynamics which are in the bottom left here. So the freshwater pulse turned into a flow of fresh water or semi-fresh water, low salinity water, stretching out into the Atlantic Ocean. When those CEPs were corrected and put on actually at the estuary points, as you can see in the top right, panel here, then the pulse of fresh water, when it goes out into the ocean, it kind of dribbles along the South American coast and hugs the coast rather than going out to sea. And that is more correct. So all of that was happening as a result of repositioning the CEPs. That shows you how it's important. I'm sure I'm losing time, so I'll skip through this, but it's very difficult to put this all together. We've got this new land-ocean coupled model, which is inserted inside the land surface model. And focusing on the UK for chamfer, this plot on the top right is, I've actually just put a dot on every one of the coastal exchange points that I have in this study. We're working at 500 meters resolution, and so it's very high resolution for us. And when you're at 500 meters resolution, for the UK, you have 8,500 coastal exchange points. And the way we're working this is I've written a script that will extract the river outflow from JULES-CaMa-Flood and produce a 1D NetCDF file, which is then passed to the ocean modelers. They run the NEMO model separately, and that calculates the sea surface height, then pass that back to me, and then I rerun JULES with integrated CaMa-Flood, impose the sea surface heights at the boundary, and then CaMa-Flood, through using the backwater effects, can simulate coastal inundation stretching into the land surface. Unfortunately, not yet published, because this is what I'm working on at the moment. And to be frank, it doesn't 100% work yet. I'm still testing it, but that's where we're going. We're working with a lot of collaborators and stakeholders in the UK, both governmental and non-governmental. And this is going to be published, we hope, this year as a new UK scale ocean wave river modeling system for predicting extreme sea levels at the coast. So thank you very much for your attention.
Okay, thank you, Toby. So yeah, obviously wetland and methane and the biogeochemistry is very important topic for CaMa-Flood. So I'm looking forward to see further progress with research. So I'd like to move to the next presenter. And unfortunately, Wen Chao cannot make a talk on time, so I'd like to share her video.
Hello, everyone. This is Wen Chao Ma. I'm from Nanjing Normal University and the University of Tokyo. Here I will present our article published in 2024, show a detailed case study on the application of the CaMa-Flood in the TDISR system. A new generation of hydrological condition simulator, TDISRs, which is jointly developed by the University of Tokyo and JAXA. T currently designed into two regions, global and Japan. Japan, which is a high spatial resolution version, and here we introduce the global one. By using several satellite products and reanalysis data, today's Earth conducted both land surface model and river routing model to simulate global hydrological conditions in near real time. So the system combines two key models, Matsushiro and CaMa-Flood. We can see the interface here and access it through this link. As of 2023, when we prepared this paper, there are three versions of forcing data employed by the T Global that introduces article, GRA 55, GSMAP, and MODIS. This data size allow TE to generate long-term near real-time outputs. And table 2 shows the summary of the validation of TEG. We can find that three key variables were used to validate TE performance: snow depth, soil moisture, river discharge, and the details of the index can be found from this table. This slide presents the overall performance of the annual mean snow amount in GRA 55 version and the latitude comparison among these three versions in 2013, as well as comparison of the monthly average of snow amount from 2001 to 2021. In Figure 3, we show a case comparison between observed and simulated snow depth results. Here, we can observe the overperformance of soil moisture, the annual mean values, and the latitude comparisons among three versions in 2013, and the comparison of monthly average of soil moisture across different layers from 2001 to 2021. Figure 5 shows the comparison from a randomly picked location. And similarly, here shows the performance of the river discharge results and the validation results for daily river discharge by comparing with the GRDC data set. By the end of 2023, the development of the 0.25 degree global version had matured and was introduced in this paper. We can find the comparison here. And now efforts of the group underway to develop higher spatial resolution and forcing data. All outputs are freely accessible, meaning that we can find more than 70 parameters on the TE page. Among many applications, well, as you can see, about flood and disasters from the homepage, a noteworthy achievement is that TE has been recognized by the WMO as a global hydrological modeling system, as illustrated by the two fingers on the right side. It was to take a deep dive on the TE data to explore additional applications related to real-world issues such as disasters. And thank you.
Okay, thank you very much, Wenchao-san. And yes, so time is limited, so I'd like to move to next talk. So next one is by Prakat. Could you please share your screen and start your talk?
Yes. Am I audible?
Yes, please change your screen to presentation mode.
No, it's okay.
Yes.
Yeah, hello everyone. I'm Prakat and I will be talking about the multivariable integrated evaluation of hydrodynamic model. This work was done when I was a PhD student in Yamazaki lab. So as Dr. Zhang said earlier, like most of the models are calibrated or evaluated against the discharge, but they have limitations in the limited number of observations in space and time, and the problem of equifinality can happen. And also, if you evaluate the model based on a fewer variables, we can have the difficulty to trace errors. And this can be overcome by considering other variables like water surface elevation, flooded area, which can be remotely sensed. And we can also try to find out like what are the different sources of uncertainty towards the different variables, which can further improve our model. So basically, we try to answer the two questions. First is like, what is the effect of combining multivariable performance on model evaluations and how it affected by baseline topographic data? Because our main hypothesis is like a better dam should improve the multiple variables at the same time. So to do this, like we perform the CaMa-Flood model simulations, which can give the output for like multiple variables: discharge, water surface elevation, flooded area, and flood extent. And we consider the observation from the various sources like discharge, water surface elevation, flooded area, but how to combine them. So as we know, like they have like the problem with the different dimensions. So the discharge and water surface elevations are like point observations, but flooded area and flood extents are like two-dimensional. So we opted like the sub-basin approach, where we divide the whole basin into like sub-basin. Here we can say like gray lining is smaller sub-basins, and we done the evaluation for each variable separately using normalized NSC values. And first we have computed the sub-basin skill score and then the overall basin skill score to evaluate the model objectively. To consider the uncertainty in the model, we basically perturb the river channel depth. So for perturbation, we kept the river depth at the mouth like constant and change the gradient along the river. And by doing this, like we consider all like the uncertainty from the river bathymetry. So our result shows like when we perform both the single variable evaluations and then a multivariable evaluation, we saw like discharge faces a large sensitivity issue, and a lot of parameters get the similar performance and faces the equifinality problem. But when we consider like water surface elevation and flooded area, we find like the optimal zones, like larger optimal zones for SRTM and 2 optimal zones for the merit, and the single optimal zone for like SRTM merit for the flooded area. But when we consider like multivariable integrated evaluation, we found like the optimal zones decreases, like basically 2 optimal zones, and then the 1 optimal zones considering the merit. So we can clearly see like the multivariable integrated evaluation reduces the equifinality problem, especially with the error removed topographic data. We also perform the CAMA with the different Manning coefficient. So we see like 0.02, 0.03, and 0.04. And what we found is we found a similar OSK values for both, and it's basically happening because of compensation of performance of different variables. So we can see like if there is an increase in the performance of flooded area, then decrease in the performance of water surface elevations. And this is mainly observed, this large variation is observed mainly in the back topographic. And it also shows that if we consider only one variable, there might be chances we are getting good results due to the wrong regions. So the main conclusions are like single variable evaluation is inadequate due to the low sensitivity towards bathymetry, and good performance may be outcomes potentially arising from the wrong regions. Second thing is like OSK approach, it can integrate multiple variable, which overcomes the problem of like limited observations in space and time, and it can do the objectively like sub-basin and basin scale model evaluations. We also found like using this approach like multivariable integrated evaluation, we can reduce the equifinality problem, especially with better topographic data. So that's all. Thank you. If you have any comments or question, you can contact me here.
Okay, oh, thank you very much, Prakat. So yeah, using satellite for evaluating the simulation, that's something CaMa-Flood achieved. I'm very happy to see this progress. Okay, so let's move to the next talk. It's by Shudon-jo again, but focusing on another aspect of CaMa-Flood.
Hello again. So this work was done in 2022. It's about correction of the river bathymetry parameters using the stage discharge rating curve. And we know that for the CaMa-Flood modeling, the bathymetry or the river depth is very important parameters in the model. But the river bathymetry is very difficult to be measured either in on the ground or from the satellite technologies. So in the model, we always use a power law function, which is a parameter with the mean river discharge. We know this is not perfect in the global area. So what we want to do is to try to use the measurement of the river discharge and the water surface elevation to do a correction of the river bathymetry. But in the when we work on this paper, we found that the river water elevation is combined, in fact, impacted by the river bathymetry, either in the river bathymetry, also the bias in the runoff input. We can see from the right figure, if we use different runoff input, we can generate different simulations of river discharge and also the water surface elevation. But occasionally, when we compare the rating curve, which means the water surface elevation and the relation between the water surface elevation and the river discharge, we found whether we use a different runoff input or the simulations are following the same curve, but it has different. It doesn't follow the observations, which is the curve in black. But from this figure, we know that this biases between the two curves is independent from the runoff input. And if we use this difference between the two curves, maybe we can have the better result for correcting the river bathymetry. So in this paper, we have introduced two methods. The conventional one is just to use the water surface elevation observation from the remote sensing to correct the river bathymetry, but the second method is using the difference between these two curves. And we applied this method in Amazon River, where has a lot of observations of river discharge and the in situ simulation of the water surface elevation. And for the experimental designs in this case, we used for the experiment 2 that we have experiment 1. We have corrupted runoff, 5 corrupted runoff. The one is minus 50%, minus 25%, and we have the 5 figures, 5 points here. And then we see if we measure the rating curve bias, when we use different runoff, the bias is almost the same. But if we use the time series bias, which is the conventional method, we can have different bias at different scenarios of runoff input. So this is the special distribution of the rating curve bias. We use an interpolation method to have the bias corrected value from between 2 points where have the pair of observation in river discharge and the water surface elevation. So when it goes to the correction of a river bathymetry in the conventional method, we can have the result in the blue line. If we use a different runoff input, we can see the blue lines are diverging in a large degree. But when we use the rating curve method, the different rating curve, corrected rating curve, almost converge in the same way. But in the downstream of this river, this might be affected by the backwater effect from the mainstream, and it has a little bit larger divergence for the result. And when we use the corrected river bathymetry to recalculate the water surface elevation and the river discharge again, we can see using different runoff, we have the bias in the discharge, but the correction of river bathymetry didn't change the bias in the discharge a lot. But for the time series bias, if we can see here when we use the when we corrected the river bathymetry, the better result we can achieve. But for instance, this is the conventional method. This is the rating curve method. When we have the result is better in the when we apply the runoff, the reasonable runoff, but for the corrupted runoff, we still cannot get the better simulation. This is more reasonable. And the third rule is when we apply the correction to the river bathymetry, we can still get the similar rating curve bias even before the correction and after the correction. So we can see that the method is more robust. And for the summary, in this paper, we estimated the bias of the water surface elevation through 2 methods and applied the linear interpolation to specially correct the river bathymetry. And we found that rating curve method is independent from the runoff bias, and it improves the water surface elevation in terms of the reliability and robustness. But this method also have some limitation that it relies on the observations of discharge, so it cannot apply to the global scale. So we still need to find other better solution. Thank you for your kind attention.
Okay, thank you very much, Shudon. So yeah, bathymetry calibration is now a big issues in CaMa-Flood. So Yeah, I appreciate your work, and let's expand this framework to the global scale. So next is session 2C, and I invited 7 speakers